Welcome to qnawire.
5 moles of a monatomic ideal gas have an initial pressure of 2.5 times 10 to the 3 pascals and an initial volume of 2.1 meter cubed. While undergoing an adiabatic expansion, the gas does 1,480 joules of work. What is the final pressure of the gas after the expansion? So this problem is very short, but I think it actually requires a few steps in order to get the answer to it. Before I solve it, let me just quickly get down the quantities that are given to us. So N is 5 moles. Pressure is 2.5 times 10 to the 3 pascals, which is kind of low pressure. 10 to the 5 is atmospheric. V initial is 2.1 meter cubed, and the work done is 1480 joules, and that's a 4. Okay, wonderful. So our goal is to get the pressure. So first, I want to write down an equation that encapsulates that it's an adiabatic process. So maybe captures would have been a better word. I'm going to cordon this off because it's going to get sort of complicated. And I'm going to number each step as well, just so it's clear. So if it's adiabatic, by definition, that means that Q is 0. So there's no heat added or subtracted from the system. So as we start many thermal problems, you write delta U is Q minus the work done by the gas. And then we set this equal to 0. So what this immediately tells us is that the change in internal energy is minus 1480 joules. Okay, so what can we do with that information? In step 2, we know that, so given that for a constant number of moles, delta U equals 3/2 nR delta T, which we said was equal to minus the work done by the gas, we can obtain that delta T is equal to minus the work done by the gas divided by 3/2 nR. So that's minus 1480 joules divided by 3/2 times 5 times R, which is 8.31 joules. And then this was mole, joules per mole Kelvin. And if you plug that into a calculator, you should get minus 22 Kelvin. Okay, so now at least we know the change in temperature, so that we're one step closer to getting the pressure. So for the third step, we want to relate temperature to pressure using the ideal gas law. So, so actually, no, sorry. For the third step, we want to get the initial temperature. And I guess we could have done this at any point, but this is towards, of course, relating temperature and pressure. So if you rearrange the ideal gas law, which states PV equals nRT, you get T initial is P initial V initial over nR. And if you go ahead and calculate this, it's 2.5 times 10, to the 3 pascals times 2.1 meter cubed. And that's all divided by 5 moles times 8.31 joules per mole Kelvin. And then if you do that, you get 126 joules. Ooh, that's 6. Okay, so you got 126, excuse me, not joules, Kelvin, which is really low because room temperature is 273, but we can also recall that the pressure is actually quite low. And then now we can get T final, given that we know the delta T from here. So I'll just like write it in red, just so it's clear. 120, it's 126 minus this 22. And these are both Kelvin. And that gives you a T final of 104 Kelvin. All right, next stop on this chain. So again, we can use the ideal gas law to get, we can use the ideal gas law to get the pressure. So we would use P equals nRT over V, but we do not know the final volume. So there's one more, so we have to find the final volume before we can use the ideal gas law. So to find the final volume, you just want to use this equation from the book, and I can tell you what page it's on. It's on page, it's in the adiabatic section, and it's equation 19.22. So I just algebraically manipulated that equation. So, and I'll write what that algebraic manipulation looks like. So you get T initial over, this is for adiabatic processes, forgot if I said that, to the 1 over gamma minus 1 times the initial volume. And we have all the ingredients to solve for the final volume. And so if you kind of running out of room, but if you kind of plug in, maybe I'll just kind of draw arrows. Well, I'll write it out. So you have this 126 over 104. And then we have gamma. So gamma is the ratio of the heat capacities. And if you look on page, let's see, 633 in section 19.7, you get for an ideal monatomic gas that gamma is 1.67. So I'm going to just like kind of scoot that into the givens up at the top. So gamma is 1.67. So then you do 1 divided by 1.67 minus 1. And then you want to multiply that by the initial volume, which is 2.1. And with that, you got 3.8 meter cubed. Does that answer make sense? So the volume got bigger. If the work was done by the gas, that kind of makes sense that it's pushing on its boundaries, so its volume is going to get larger. Okay, and then we finally have all the ingredients to calculate the pressure. So I'll label that step 5. Last but not least, pressure is nRT over volume. And again, that's just from manipulating the ideal gas law. Okay, and I am like kind of out of room. So T final, I'll just kind of draw like little arrows for everything. So T final, you plug in from here. V final comes from here, and then N is 5 and R is 8.31. And that is equal to 1.1 times 10 cubed pascals. And so the pressure, looking at this answer and trying to figure out if it makes sense, we can see that the pressure got smaller. So as the gas expands, I can see that kind of being true on a microscopic scale. And it's definitely on the order of magnitude of the original pressure, which is also a good sanity check.